Module 1, Lecture B, Python Refresher. By the end of this lecture, you will be able to write clear Python functions that process small civil engineering datasets, use lists, dictionaries, loops, and simple comprehensions to organize engineering records, and read, write, and debug simple data processing scripts for local files. Readable Python functions. Function basics. In Python, a function is a reusable set of instructions for a specific task. In civil engineering data work, functions help avoid repeating common steps like converting measurements, calculating averages, or summarizing data. By defining these tasks once, engineers can keep scripts clearer and focus the main workflow on the overall process. A good function should do one clear task, and its name should make that purpose obvious. This is especially important in engineering scripts, where others may review, share, or modify the work and need to trust the results. Keeping functions focused, such as separating data summaries from maintenance checks, reduces confusion and makes mistakes easier to find. Functions make scripts more reliable by separating logic into parts that are easier to test and debug. In civil engineering, this helps confirm that calculations work on known data before using them for decisions. Clear functions also make data flow and results easier to understand, producing code that is concise, transparent, and maintainable. Python code. Function basics. Functions help make engineering calculations reusable, while small datasets are useful for practice. Using clear names also makes scripts easier for colleagues to review. This function converts a list of measurements from millimeters to meters. If the list is empty, it simply returns an empty list to avoid unnecessary processing. Otherwise, it divides each value by 1000 and returns the converted list, keeping the function focused on a single unit conversion task. This code creates a new list by dividing each millimeter value by 1000, converting the data to meters. Using a list comprehension makes the conversion concise, readable, and efficient for engineering calculations. The average strength function calculates the mean strength from a list of values measured in megapascals. If the list has no values, it returns no result to avoid an invalid average. Otherwise, it adds the values, divides by how many there are, and returns the average. This calculation finds the average strength in megapascals by adding all the strength values and dividing by how many values there are. It gives the mean strength, a basic measure often used in engineering calculations. The classify pavement function evaluates a pavement score and assigns a condition label. If the score is 85 or higher, it labels the pavement as good, using a predefined threshold to support pavement quality assessment. This code labels pavement condition as fair when the score is at least 60. It is part of a function that converts numerical pavement scores into simple quality categories for easier interpretation. The function labels pavement condition as poor when the score is below 60. This return value marks pavement that falls short of higher quality standards. We set up 3 small civil engineering datasets: settlement measurements in millimeters, concrete strength values in megapascals, and pavement condition scores linked to site identifiers. These datasets will support later examples involving unit conversion, averaging, and classification. The process first converts settlement measurements from millimeters to meters by dividing each value by 1000. It then finds the average concrete strength by summing the strength values and dividing by the number of measurements. Finally, it classifies each pavement site as good, fair, or poor based on its score, storing the labels in a new site condition dictionary. The output reports the converted settlement readings in meters, the average concrete strength in megapascals rounded to 2 decimal places, and the pavement condition labels based on their scores. It ends by showing that functions make the program easier to read by keeping each task small and modular. This script shows how small, clear functions can handle basic engineering calculations. It converts settlement measurements from millimeters to meters, finds the average concrete strength, and labels pavement conditions as good, fair, or poor based on their scores. The output gives the converted values, the rounded average strength, and the condition label for each site, demonstrating code that is easy to read and maintain. Function inputs. In civil engineering functions, clear inputs define what information the function uses and what task it performs. Inputs may include measurements, material properties, dataset names, or limits for flagging results. Passing these values directly, rather than relying on hidden data, keeps the function focused, predictable, and easier to test across different datasets. Name function inputs to reflect the engineering problem, not just the programming task. Descriptive terms such as pavement thickness or rainfall depth make the purpose clear and help prevent mistakes. Also make clear whether each input is a single value or a collection of records, so functions can be reused reliably across similar analyses. Design functions to use only the inputs they truly need. For example, a function that summarizes survey elevations should take elevation data, not an entire project database. This makes debugging easier, supports testing with small examples, and helps others understand and trust the function, especially when civil engineering data may be incomplete or inconsistent. Python code. Function inputs. Functions should use clear engineering inputs with names that describe the civil data they handle. Keeping inputs small makes the functions easier to test. The summarize deflections function takes deflection measurements and a service limit, then prepares the data for comparison. It begins by creating a list to hold only valid numeric deflection values, so later calculations use clean and reliable input. The code reviews each deflection value and keeps only entries that are numeric, such as integers or floats. These valid measurements are collected into a new list, while non-numeric entries are excluded from further analysis. The code first checks whether any valid numeric measurements are available. If none are found, it returns a clear default result with a count of 0, no average, and no flagged values. This prevents errors and keeps the output consistent when the data cannot be used. A simple engineering summary reports the average valid deflection to show the typical response, then checks which valid deflections exceed the service limit. Any values above the limit are flagged for review because they may indicate issues needing attention. The function returns a dictionary that summarizes the deflection data for reuse. It reports how many valid numeric values were found, gives their average rounded to 2 decimal places, and lists any values that exceed the service limit. This structure makes the results easy to interpret and process further. We create a small set of beam deflection measurements in millimeters, including one missing value. We also set an allowable deflection limit, which provides the threshold for judging whether the measurements are acceptable. The summarize deflections function takes beam deflection measurements and an allowable deflection limit, then stores the results in a summary. The summary reports how many measurements are valid, their average deflection, and which values exceed the limit. This makes the deflection data easier to review and use for analysis or reporting. The output presents a readable summary of the function input and results. It reports the number of measurements, the average deflection rounded to 2 decimal places, any deflection values above the allowable limit, and the limit used for comparison. This script analyzes beam deflection measurements by ignoring non-numeric entries, then calculating the average of the valid values. It also identifies any deflections that exceed the service limit. The output gives the number of valid measurements, the average rounded to 2 decimal places, the exceeding values, and the limit for comparison. Function inputs. Function inputs define the data a function needs to work correctly. In civil engineering, these inputs might be measurements, material properties, or inspection results. Making inputs explicit keeps the function predictable, easier to test, and more reusable because it avoids hidden values and clearly shows what information is required. Name function inputs for their engineering meaning, not just their programming role. Clear names such as pavement thickness or rainfall depth help show what the function is meant to do. Keep each function focused by including only the inputs needed for its task, so it stays clear, specific, and free of unrelated details. When designing function inputs, focus on the data's format and reliability. Civil engineering data may include missing values, inconsistent units, or readings from different sources, so functions should make clear assumptions and check inputs when needed. For example, a function should know the units of settlement readings and whether they come from one instrument or several locations. Careful input design makes scripts easier to debug, update, and trust for engineering decisions. Python code. Function inputs. Good functions start with clear inputs. Meaningful input names make their purpose easier to understand, and simple checks help make the function safer to use. The summarized deflections function takes deflection readings and a service limit as inputs. It prepares to compare the readings against that limit by first creating a list for valid values, which will hold only the numeric deflection data used in the analysis. The process filters a list of deflections by keeping only values that are numeric, such as integers or floats. These valid readings are collected into a new list for analysis, while non-numeric entries are ignored. If no valid numeric readings remain, the function exits safely with a clear default result. It reports 0 valid readings, no average deflection value, and no flagged status. This prevents errors and handles missing data gracefully. The code finds the average valid deflection in millimeters, then compares it with the service limit. If the average is above that limit, it marks the deflection as unacceptable, so the issue can be identified quickly. The function returns a dictionary with 3 reusable results: the number of valid numeric readings, the average deflection in millimeters, and whether that average exceeds the service limit. This makes the key measurement summary easy for other parts of the program to use. We create a small beam deflection dataset in millimeters that includes numeric values along with a missing entry and a text entry to reflect messy real-world data. We also set a service limit, which acts as the threshold for judging whether the average deflection is acceptable. This prepares the data for checking deflection performance against the limit. The summarized deflections function takes beam deflection readings and a service limit, then summarizes the usable data. It ignores non-numeric values, finds the average valid deflection, and checks whether that average exceeds the limit. The summary reports the number of valid readings, the average deflection, and whether the service limit is surpassed. The output reports how many deflection readings were valid, then shows the average deflection in millimeters rounded to 2 decimal places. It also states whether that average exceeds the service limit, making it clear whether the deflection is acceptable. The script cleans a set of beam deflection readings by keeping only numeric values, then calculates the average and compares it with the service limit. In this example, it finds 5 valid readings with an average deflection of about 9.14 millimeters. Since this is above the 9 millimeter limit, the result indicates that the limit is exceeded. Core containers, lists. Python lists store related values in a specific order, making them useful for civil engineering data such as rainfall, concrete strength, or traffic counts. Because they preserve sequence and can hold different types of information, lists provide a flexible way to organize engineering data before analysis. Lists are useful in engineering because they make it easy to process data step by step. Engineers can store measurements, compare them with thresholds, update them as conditions change, and summarize results. Whether tracking inspections or analyzing vehicle counts, lists help turn raw data into practical insights. Lists organize data clearly and work especially well with loops and comprehensions. Loops apply the same action to each item, while comprehensions provide a compact way to transform or filter data. In engineering tasks such as handling test results or survey data, lists help keep datasets ordered, accurate, and ready for more advanced processing. Python code. Lists. Lists keep engineering measurements in order. Loops apply the same processing to each value, and comprehensions provide a concise way to create cleaned or derived lists. Daily rainfall measurements are stored in an ordered list, with each value representing rainfall depth in millimeters for 1 day. Keeping the data in order makes it easier to access, process, convert, or analyze later. A list of station labels, from A through G, is created to identify each inspection station. These labels help connect each station to its rainfall measurement so the data can be organized and processed later. The code first checks that the rainfall measurements and station labels have the same number of entries. This confirms that every measurement can be matched to a station. If the counts do not match, it raises an error to prevent incorrect pairings later. A list comprehension converts each rainfall measurement from millimeters to inches by dividing by 25.4. Each converted value is rounded to 2 decimal places, producing a new list in the same order as the original. A list comprehension can identify stations that may need a drainage review by checking rainfall measurements against a 15 millimeter threshold. As each measurement is examined, its position is used to match it with the correct station. The result is a new list containing only the stations where rainfall met or exceeded the threshold. To find the total rainfall, start with a running total set to 0. Then go through each rainfall measurement and add it to that total. By the end of the loop, the total represents the sum of all daily rainfall values. Average daily rainfall is found by dividing the total rainfall by the number of recorded days. Using the length of the rainfall list makes the calculation work automatically for any amount of data. The output first shows the raw rainfall measurements in millimeters, then converts them to inches for easier comparison. It also reports the total rainfall and the average daily rainfall, rounded to 1 decimal place. Finally, it identifies any stations that need further review because their rainfall exceeds the chosen threshold. The script summarizes rainfall data for inspection stations. It first confirms the rainfall and station lists match, then converts measurements from millimeters to inches. It also identifies stations with more than 15 millimeters of rain, calculates the total and average rainfall, and prints these results to highlight stations that may need review. Dictionaries. Python dictionaries store data as key value pairs, making them useful for organizing records in civil engineering. For example, a bridge ID can point to inspection ratings or maintenance status. Because data is accessed by meaningful labels instead of list positions, dictionaries make scripts clearer, faster to use, and less error-prone. Dictionaries organize engineering data by pairing clear labels with values, making records easier to understand and debug. They can also be nested to manage related measurements, such as grouping data by station number. This structure is best when you need to quickly find the right record, and it helps turn raw data into useful information for analysis and visualization. Use dictionary keys that are stable, unique, and meaningful, and keep values stored in a consistent way. This reduces errors and makes the data easier to process. Dictionaries are especially useful with loops and comprehensions for organizing labeled technical records and preparing them for analysis. Python code. Dictionaries. Dictionaries organize engineering records by pairing each key with a related value. The key identifies an asset or sample, while the value stores its measured information. A dictionary, called bridge ratings, stores inspection scores for different bridges. Each bridge is identified by a unique text key, such as BR-101, and its value is an integer rating, such as 7 or 4. This makes it easy to look up and manage each bridge's condition using its identifier. The code creates a dictionary that connects each bridge identifier to a condition rating. For example, BR-318 has a rating of 6, while BR-422 has a rating of 3. This makes bridge condition data easy to look up and use for tasks such as maintenance planning or analysis. The process selects bridge BR-205 and uses that identifier to look up its condition rating in the bridge ratings dictionary. The retrieved rating is then stored so it can be referenced easily for that specific bridge. A bridge records dictionary can store detailed information for each bridge by using the bridge identifier as the key. Each identifier points to a nested dictionary containing attributes such as rating and span in feet. This structure keeps related data together and makes each bridge record easy to access and manage. The code continues building a bridge records dictionary, where each bridge code maps to its details. It adds records for bridge BR-318 with a rating of 6 and a span of 140 feet, and bridge BR-422 with a rating of 3 and a span of 60 feet. This keeps each bridge's information organized and easy to access later. Create a maintenance list by filtering the bridge records for bridges with condition ratings of 4 or lower. A list comprehension checks each bridge record and keeps only the identifiers for bridges that need attention. This condition filters for bridges that may need maintenance by selecting those with ratings of 4 or lower. These lower ratings indicate poorer condition and help identify bridges that require attention. The process begins by setting a running total to 0, then going through each bridge record and adding its rating to that total. This gives the sum of all bridge ratings, which can then be used to calculate an average or support further analysis. To find the average bridge condition rating, count the total number of bridge records, then divide the accumulated total rating by that count. The result is the average condition rating across all bridges in the dataset. The output shows the selected bridge and its rating, then lists the bridges that need maintenance based on ratings of 4 or below. It also reports the average rating across all bridges, rounded to 2 decimal places, giving a quick summary of the dataset's overall condition. This script shows how dictionaries can organize bridge inspection data. It stores bridge ratings, retrieves the rating for bridge BR205, and then adds span details using a nested dictionary. It also finds bridges with ratings of 4 or less as maintenance candidates and calculates an average rating of 5. The final output summarizes the selected bridge rating, the maintenance list, and the overall average. Sets. In Python, a set is useful when you need unique values and do not care about order. In civil engineering data, sets can remove repeated items such as bridge IDs or road segment names, making it easier to see which identifiers, sites, or materials are present. Because sets focus on membership and distinctness, they are best for comparing groups and finding unique elements in a dataset. Sets are useful for quickly checking whether values belong in a collection, which makes them effective for validating engineering data. They can help find missing or unexpected station, inspection, or asset identifiers by comparing data against an expected list. Sets also make it easy to identify shared or unique values across datasets, supporting efficient data reconciliation and project overlap checks. Sets are best for managing unique, stable values such as strings or numbers, while dictionaries are better for complex records with multiple attributes. In engineering data analysis, sets can help identify distinct items like defect types or inspectors and compare them with total records. This makes it easier to spot duplicates, data entry issues, and patterns related to uniqueness or membership. Python code. Sets. Sets are useful for storing unique engineering identifiers. They also make it easy to check membership for data validation and compare datasets to find differences. A list of bridge inspection identifiers is created with some duplicate entries to represent repeated records. This sets up a simple example where the list can later be converted into a set, so each bridge identifier appears only once. Convert the bridge inspection identifiers into a set to remove duplicates automatically. This keeps each identifier unique, supporting accurate data analysis and validation in engineering work. A set of official bridge inventory identifiers stores each bridge ID, such as B101 through B104, only once. This makes it easy to confirm whether an identifier is included and to compare the inventory with other sets of bridge IDs. To validate the bridge data, compare the observed bridge identifiers with the official list. Official bridges that do not appear in the observed set are marked as missing, while observed bridges that are not in the official list are marked as unexpected. This highlights discrepancies between the two records. To find bridges that are both observed and officially recognized, compare the two sets of bridge identifiers and keep only the values they share. This intersection creates a matched set of common identifiers, making it easy to validate the data and check for consistency. A list of pavement materials may contain repeated items such as asphalt. A set comprehension can be used to keep only the unique materials, removing duplicates, and leaving a collection of distinct pavement types. The output summarizes the inspection data by first showing the total number of recorded bridge entries and the unique bridge identifiers found. It then compares the observed bridges with the official list to identify matches, missing official bridges, and unexpected entries. Finally, it lists the unique pavement materials found during inspections, giving a quick view of material variety across the sites. This script shows how sets can manage engineering identifiers efficiently. It turns bridge inspection records into unique entries, compares them with an official list to find matches, missing items, and unexpected items, and also extracts unique pavement material labels. The output summarizes record counts, bridge comparisons, and material types, demonstrating how sets support fast uniqueness checks and comparisons. Files and debugging. Reading local files. Reading local files in Python is an important skill for engineering work because data often begins on a computer or shared drive. To use that data correctly, a script must find the file, open it, and interpret its format, such as plain text or CSV. The key habit is to know where the file is stored, what type of data it contains, and how to preserve its structure for later processing. When reading a local file, treat it as structured records, not just text. In engineering data, each line may represent a meaningful observation, so Python can process it line by line or load it for analysis. Always check headers, missing values, units, and context to make sure the data still matches its original engineering meaning. Reading a file successfully is not enough. Careful inspection helps prevent analysis errors. When reading files in Python, expect real-world data problems such as wrong paths, inconsistent names, incorrect delimiters, text where numbers are expected, or blank lines. These issues are common in engineering data, not necessarily Python errors. To avoid unreliable results, always inspect the first records, confirm row counts, and check that key fields are correct before using the data for analysis. Python code, reading local files. When working with local engineering files, read them safely and check the records before relying on the results. Be prepared to handle missing files and invalid values so the analysis remains reliable. The script begins by importing tools for file handling and data processing. The CSV module lets the program read and write structured CSV data, while Path from pathlib provides a platform-independent way to work with file paths. The pathlib path class is used to create a cross-platform reference to a local bridge inspection CSV file. This path object makes it easier to store or retrieve the inspection data without worrying about operating system differences. The data is organized as a collection of bridge inspection records, where each record stores a bridge identifier, span length, and rating. It includes 3 bridges, with one record showing a missing span value. This structure makes the inspection data easy to manage and process later. To save records as a CSV file, open the target file for writing so any old content is replaced. Use a dictionary-based CSV writer with the column names taken from the first record's keys. Then write the header, followed by all records as rows, creating a structured and readable CSV file. The process begins by creating an empty list to hold records that are successfully read and verified from the file. It also starts a counter at 0 to track records with missing span values, helping identify incomplete data. The code first confirms that the target path exists and is a real file before trying to read it. It then opens the file using UTF-8 encoding and reads the CSV data, so each row can be handled by column name. Finally, it checks for required columns to make sure the file has the expected structure before continuing. The code first confirms that the CSV file contains the required columns, ensuring the data has the expected structure before processing. It then reads each row and extracts the span in feet and rating values, removing extra spaces so the data is clean and ready for validation and conversion. The code checks whether the span text is empty. If it is, the record is treated as missing data. The missing value count is increased, and the record is skipped. This helps ensure that only complete records are processed. The code prepares bridge data by converting the span to a floating point number and the rating to an integer. It then stores these validated values with the bridge ID as a record for later analysis. If required columns are missing or the file cannot be found, it prints an appropriate error message. Count the verified records by finding how many loaded records there are. Then calculate the average span by adding the span values for those records and dividing by the record count. This gives a concise summary of the verified data in feet. The output summarizes the processed data by showing the source file, the number of verified records, and how many missing span values were skipped. It also reports the average span for the verified records and displays the first verified entry as a quick check of the data's structure and content. This script shows how to read and validate bridge inspection data from a CSV file. It checks that required columns are present, converts span and rating values into numbers, and skips records with missing span data. It then reports a concise summary, including how many records were verified, how many were skipped, the average span, and the first valid record. The main goal is to process the data safely while protecting against missing values and incorrect file structure. Writing local files. When a script writes local files, it turns temporary results into lasting records. These files should be clear, consistent, and useful for future readers, whether they are plain text logs or tabular data. Meaningful file names, clear column names, and consistent units help turn raw output into information people can understand and trust. When writing files, first decide the save location, file name, and whether existing content should be replaced. Overwriting may be acceptable in a classroom, but in professional work, it can erase important data if backups or clear naming are not used. Use file names that distinguish dates or locations. Confirm the destination folder and write permissions, and know whether your script is creating, appending to, or overwriting a file. When writing files, use a consistent format so the data is clear, accurate, and easy for other programs to read. Add enough context, such as titles, headings, and timestamps, so the file can be understood on its own. After saving, always inspect the output and compare it with the original data, because formatting problems often appear only when you review the file carefully. Python code. Writing local files. This example creates a small engineering CSV file using simple bridge inspection records, then verifies that the saved output contains the expected data. The script starts by importing tools for working with files and CSV data. The path class helps manage file paths in a convenient cross-platform way, while the CSV module supports reading and writing CSV files. Together, these imports prepare the script to locate files and process tabular data. The inspection data is organized as a list of records, where each record describes one bridge span. Each entry includes a unique span identifier, the crack measurement in millimeters, and a condition rating, such as good, monitor, or repair. This structure makes the data easy to manage, process, and store. A new dictionary is added to a list of inspection records to represent one bridge span. It identifies span A3, records a crack width of 2.1 millimeters and marks the span as needing repair. This record can later be written with the rest of the inspection data to a CSV file. A local output folder is defined using a path object, and the CSV file name is added to create the full save location. This ensures the bridge inspection summary file will be written to the intended directory. The code makes sure the output folder exists, creating it along with any missing parent folders and avoiding errors if it is already there. It then defines the field names that match the record keys so they can be used as CSV headers and keep the written data organized. Open the output file for writing with a context manager so it closes automatically when finished. Then, create a CSV dictionary writer using the chosen field names, which define the file's columns. Finally, write the header row so the CSV is ready for data rows to be added. The CSV writer can write a list of dictionary records to a file in one operation. It converts each dictionary into a row using the previously defined field names, so the data lines up with the header. This keeps the output structured and consistent. To debug a saved file, open it in read mode and use a context manager so it closes automatically afterward. Read the full contents and split them into separate lines, making it easier to inspect each line individually. The code checks whether the saved CSV file has the correct number of lines. It compares the expected total based on the number of records plus the header row with the actual lines in the saved file. This helps confirm that the file was written correctly and kept the intended structure. The file check confirms that the saved data is complete and correctly written. It reports where the file was stored, compares the expected and actual line counts, and briefly inspects the header and first data row. If the counts match, the check passes, indicating the saved file is intact. The script creates a folder for output, writes a CSV file of bridge inspection records, and then checks that the file was saved correctly. Each record includes a bridge span identifier, crack size, and condition rating. After writing the data, the script reads the file back, compares the actual line count with the expected header and data rows, and prints key details to confirm whether the check passed. Debugging file scripts. When debugging scripts that read files, first question your assumptions about the file rather than the calculations. A script may work on a sample file, but fail on real data because the file name, location, blank lines, delimiters, or structure are different. Check that the file can be found and opened, that its format matches the reading method, and that the first records look as expected. This often reveals simple file mismatches before you spend time on unnecessary debugging. After opening a file, the key task is turning raw text into reliable data. Because files may store dates, measurements, missing values, or comments as plain text, clean and check each value before using it in calculations. Debug by verifying what your script reads, separates, converts, and stores. Effective debugging starts with writing scripts that make problems easy to find and safe to handle. Scripts should state their assumptions, keep data reading separate from processing, and give clear error messages for issues like missing files or unreadable values. Testing should begin with small, checkable files before moving to more complex cases. In engineering, this makes debugging a professional skill that improves reliability and transparency. Python code, debugging file scripts. When debugging file scripts, start by checking your assumptions. Small civil datasets make errors easier to find. and clear messages help engineers trust the processed results. The script starts by importing tools for working with files and CSV data. It uses the path class to handle file locations consistently across operating systems, and the CSV module to read and write comma-separated data. Together, these imports prepare the script to manage bridge inspection data files. A small bridge inspection dataset is created for debugging. It is saved as a CSV file and includes rows for bridge components and their defect counts. The first row defines the column names, followed by sample entries such as a deck with 3 defects. The snippet creates sample CSV-style rows to test data cleaning and debugging. It includes component defect counts with common issues, such as extra spaces around a number, a missing or non-applicable value, an incomplete row, and a repeated component whose count should be combined with an earlier entry. The script opens a file for writing, clearing any existing content, then uses a CSV writer to save a predefined set of rows. This creates a small, controlled dataset that can be used to debug the script and test how it handles different data cases. The setup prepares 3 tracking structures for processing bridge defect data. One stores valid defect totals by component, another counts successfully processed records, and a third keeps information about rejected records with errors, such as missing fields or unreadable data. Together, these make it easier to report both usable and problematic entries. The code first uses the path library's exists method to confirm that the expected local file is present. If the file is missing, it raises a file not found error with a clear message, helping with debugging and preventing the program from continuing without required data. The code reads a CSV file and treats each row as a dictionary, so values can be accessed by column name. It skips the header by starting with the second line, then processes each row for validation and further handling. The code safely reads the component name and defect count from the current CSV row. It uses a default empty value when a field is missing, and trims extra white space from the component name. This cleans the data, so it is ready for validation and further processing. The code marks a row as invalid if either the component or defect count is missing. It records the line number and the missing field reason in the rejected records list, then skips the row and continues with the next one. The code tries to convert the defect count text into an integer inside an error handling block. If the conversion works, the numeric count is stored for use. If it fails, because the text is not a valid number, the row is recorded as rejected with its line number and an unreadable count message. Then the loop skips to the next row. The code adds each valid defect count to a running summary for its bridge component. If the component is not already in the summary, its count starts at 0 before the new defects are added. It also increases the valid records counter to track how many valid entries have been processed. The script reports which file was checked, then summarizes the results by showing how many records were valid and how many were rejected. It also groups detected defects by bridge component to show where problems are concentrated. Finally, it lists rejected records with their line numbers and reasons, helping users debug issues and improve data quality. This script creates sample bridge inspection data, then checks and summarizes it for data quality. It verifies required fields, converts defect counts to integers, rejects incomplete or invalid rows, and logs the reasons for rejection. The valid records are grouped by component type to summarize defect totals. The final report shows valid and rejected record counts, defect summaries, and rejection details to support debugging and clear error reporting. In this lecture, you learn to write clear Python functions that process small civil engineering datasets, use lists, dictionaries, loops, and simple comprehensions to organize engineering records, and read, write, and debug simple data processing scripts for local files. In the next lecture, Lecture C, we will go over data thinking. Thank you for your attention. See you all in the next lecture.